That's not actually what people want to know. People want to know, how do things get mass from a field?
Have physicists been wrong about the Higgs boson all this time? What if it's not what we think, but something far more elusive? What does the origin of mass in the universe have to do with music?
The universe is not playing music. The universe is a musical instrument. Things happen on it. Music is happening.
Is empty space truly empty? Or is it a strange sea with invisible forces shaping our existence? What if particles of matter, like us, are just waves moving through a cosmic ocean? Here today to discuss all these fascinating questions and more is theoretical physicist Matt Strassler, who takes us on a journey into the unseen depths of the universe. We'll dive deep into the mysteries of quantum physics, the nature of space and time, and how waves, not just particles, are actually the building blocks of reality.
I don't think you can define any new concept without an analogy. You build on analogies in creating knowledge.
That will reveal how the Higgs boson, often oversimplified, may hold the key to understanding all of the forces and fields that impact our existence. Buckle up, take your Dramamine, and get ready for a wild voyage on a cosmic sea as we take a journey stranger than science fiction, where space isn't empty and the cosmos just might be playing its own symphony. Let's go.
What I wanted to do is start with a reaction. I'm going to call this game, one of the games I like to play is Deepak or Matt. And I'm going to read you two quotes. One is from Deepak Chopra, past guest, many-time guest, friend of the show. And one is from you, Professor Matt Strassler. And I'm going to ask you to tell me which is which, or who said what. Okay, here's the first one. Vibration is the inherent dynamism of the universe knowing itself that creates the creative force that we experience through the universe as a cosmic hum. And then the other quote goes like this: like any musical instrument, the cosmos resonates with a pattern of frequencies, one that can be translated directly into the bricks of the material world. The quietest tones, the universe rings everywhere in everything. Okay, so which is you and which is Deepak?
Well, the second one is me. And the similarities are striking, but the differences are also extremely important. The differences lie in the details and in the fact that the words that I used are based on mathematical equations. I am essentially translating the mathematical equations of physics into a language that everyone is familiar with, which is the language of music. And so I would say that, the notion that the universe has something to do with resonance and vibration and music, these are not obviously new ideas. These go back to ancient times. They are one of many ancient ideas. But this is an ancient idea which turns out in some way to be instantiated in the equations that particle physics have found really work for describing the world. And their differences are as important as the similarities. That is to say, there really are things that are similar to what Mr. Chopra would say, but then there are things that are different. And a cosmic hum is not one of them, for example.
He brings up something that you make clear. The origin of the word wave in Romance languages comes from undulate, ahonde, wave. And he brings up in Sanskrit, the word for vibration is spanda, which means the creative pulse of consciousness. So there might be more here than meets the eye. I want to do what you're never supposed to do, which is to play a game called judging books by their covers. And you talk a little bit about probability and experimental, so they say don't judge a book, but what the hell else are you going to go on? I mean, you and I are just meeting each other now, and I wouldn't have read it.
Every publisher knows that people judge a book by its cover, so.
They always do. And in fact, if you try to sell this book, which I would never do, God forbid, let me see what it's going for on Amazon. No, this is just a wonderful book. If you try to sell it and it doesn't have the cover, it's worth 10%. And I always used to say, when I wrote my first, who cares? How much dust is raining down on books, throughout the, it can't be that. And of course, dust is the villain of my first book. But I want to ask you, can you take us through the title, the subtitle, and the beautiful artwork on the cover, Kind of Blue? I was thinking of the musical notes from Miles Davis when I looked at it. That's Stefan's influence.
That's a connection. Yeah, I hadn't thought about that. Waves in an Impossible Sea is very much what the book is about. Space-time, the essence of the universe, is in some ways like a sea, but it has properties that no physical material sea could possibly have. And so it really is in some way extremely mysterious, and that seemed an appropriate way to characterize it. And waves in that sea are what material things like ourselves are made from. And so the point of the book is to explain how it can be that we could actually be made from waves and how ordinary life could somehow emerge from that. It's a very strange idea. It's certainly not an idea that people in the 19th century would have known how to make sense of. It's really a 20th century idea, and one that we're still coming to grips with, and that hasn't even really been, I think, widely promulgated across society. It's part of why I felt the book was important to write. I'm glad to say I'm responsible for the title. I'm very proud of that title. The publisher, of course, creates the artwork. And I think I was struck when I saw it for the first time. I mean, it's a picture of, some sort of strange kind of waves against a strange sky. And of course, the waves are the wrong shape for a physicist, but I don't care. I mean, they're beautiful. It's a beautiful cover artistically. And what's remarkable about it is there's no evidence from that title from that cover that it's a physics book. So I wondered, wow, that's kind of daring. But I think they felt that the book would carry itself over time, and the beauty of the art would draw people's attention, and the strangeness of it in the color scheme is appropriate because it's a very strange world we live in, and that's part of what I'm trying to convey.
Another great intellect who gets a lot of credit in many domains, including a lot of attention from the world's richest man, once said the following: "If you want to find the secrets of the universe, think in terms of energy, frequency, and vibration." Have you heard that quote by Nikola Tesla?
I haven't. It wouldn't surprise me, of course. I mean, the man was a deep thinker and certainly understood waves and how they are generated and how they move around and what you can do with them as well as anybody ever has. Now, what I don't know is how much quantum physics he knew and how much quantum physics he actually used. Certainly he was, in an era where this was coming up, and he may have been very well aware of it. So that's a question I will have to investigate. But, he was aware, as any physicist would be, or any engineer, that sound and light are all about the transfer of energy via vibrations, waves in general, whose frequency is essential. And so even before quantum physics, you could make a statement like that if you knew that sound and light were waves. I think what's really remarkable is to discover that not only sound and light, but also electrons and quarks also follow these principles. And that is something which only becomes possible when you understand quantum physics.
One thing I'm ashamed to ask, but I will because I feel comfortable with you, and I can be vulnerable, is that Planck's formula, famous formula, E equals h times f, you have h as a constant, Planck's constant, and frequency is a real number. How can that be equated to quanta, as you do in the book, via the Broglie relationship? How can you have something that's quantized that is intrinsically able to be related to something that is continuous, i.e. a real number like frequency?
Right. So frequency and energy are continuous quantities. The thing which is quantized is not the wavelength or the frequency of the vibration. It's the height of the vibration. So, or the height of the wave. So there are two essential quantities that are going in to waves in quantum physics. One is the continuousness, which is the wavelength or the frequency, but the other is how much energy in total can you have for that frequency? And that's set by the amplitude. And so you can have a certain amplitude or twice that or well, that's not quite true. You can have a certain amplitude that gives you a certain energy. You can have a different amplitude which gives you twice that energy, another amplitude which gives you 3 times that energy. But in quantum physics, that's all you can have, at least for photons. And so that's the distinction that goes into the quantum physics.
What is a wavicle, and how is it different from what we call wave packets?
Let me set wave packet aside. It's a different issue. So the first question is, what is the relationship between a wavicle and a wave? So a wave can have any height or amplitude. So, you can take a wave of this height, you can make it higher. In normal life, we would think you could make it lower and you could make the height as small as you want. Or in the language of light, you would imagine that you can make a light bright, or you can make it dim, and you can make it as dim as you want. And the great discovery of the 20th century was that you can't do that, that there is a dimmest possible flash of light, and that's what we call a photon. And we usually in our communications as scientists and when talking with the public will say, a photon is a particle of light. But there's a bit of a problem with that language because the word particle calls to mind a little dot, some little speck of thing moving around, right? And the problem is that's really not what photons are. It's also really not what electrons are, even though we call them particles too. And so what is a photon with respect to a light wave? Well, if I take a laser, it's a wave that's very bright. And if I were to turn it down so that it becomes extremely dim, it would eventually become the dimmest possible flash of light, which would be a wave with the smallest possible amplitude that's allowed. So you could call that a particle. It's particle-like in the sense that it's indivisible. You can't turn it down anymore, so you can't break it in half. And it can be absorbed or emitted only one at a time. So it's particle-like in that sense. But it's very not particle-like in the sense that it has a frequency and it's spread out. I mean, it's fine to take a word like particle and give it a new definition, which means something different from what we normally mean in English. We do that all the time. We change, we repurpose words. But I think it has a real disadvantage because we have such a clear notion of what particle means in English that we bring to the table too much baggage. And wavicle is nice because it's something we don't know what it means. And so therefore we are more open-minded about how it might behave. And I think that's good. Now, wave packet. A wave packet is a specific shape that a wave can take. Rather than making it very spread out, you make it kind of more compressed and it'll stay together for a while. If you take a wave packet and let it go for a long time, it'll eventually spread out. But it's a shape to a wave. And a wavicle can be made into a wave packet shape also, just like any wave can. But it's not specifically tied to quantum physics, and it's not specifically tied to wavicles.
And the impossible C, is it an attempt by you to sort of maybe come to grips with, or perhaps rectify past wrongs, which you call in this book phibs, P-H-I-B. What is a phib, and why should the average reader care about being fibbed to?
Fib is of course a little lie, and fib in the book is spelled with a PH because I'm talking about little lies told by physicists. And we tell these lies all the time, and sometimes we tell them because we have to. We tell them, when we're teaching first-year physics students, we don't tell them everything we know. It would be too much. It would be overload. We simplify things a little bit. We cut corners. We explain things partway, and we leave things out. And a lot of the time, that's a harmless thing to do. But when we are talking to the public and we tell lies of a small sort, these fibs, that in some way deeply go against how the world actually works, they're not just any more little adjustments to the facts, contradicting the facts, and making it harder for a non-physicist to understand how the world works. So I think there's a line between fibs that are, little approximations to the truth, as opposed to things that we are telling people so that they will feel they understand, whereas in fact we are misleading them. And a great example of a fib that always bothered me is when we tell people that planes fly because of Bernoulli's principle. The fact that, the air goes faster over the top of the wing is, okay, this is a complete lie. And when I finally learned how planes fly in detail, I learned in graduate school. It's pretty complicated. It involves turbulence and vortices. Okay, but fine. So it's not so easy to explain to people how planes fly. It's a complicated thing. But do we have to lie to them? That's a fib that goes too far. And so my feeling is that, my general philosophy is that if you're telling a fib as a physicist or as a scientist to placate people, to make them feel like they understand something, you're not trying hard enough. It's your fault, right? You haven't thought hard enough about how could I do this? And so a lot of writing this book was about thinking about how to explain things in ways that would not require a lie.
One thing to push back on you with love and respect are the use of analogies. In this book, it's replete with them. And the impossible C is an analogy.
It's true.
It seems to me that, you're as Nima Arkani Hamed, who's promised to be a guest on the podcast, but in 4 years has not come on, says Matt combines his penetrating insights together with a brilliant flair for beautifully clear, non-technical explanations to produce a true masterpiece with his book. I've never seen its equal. Oh my gosh, what an encomium. But there are a lot of analogies, including you start off with fields and you use analogies with waves, and you talk about iron. Can it be done? Can you define a field without an analogy?
I don't think you can define any new concept without an analogy. You build on analogies in creating knowledge. I don't want to suggest that analogies are not important. In fact, I think they're critical. And choosing the right analogy is really important because, again, if you choose the wrong one, you're now leading people down the wrong path. So I would say that one of the key jobs that I had as a writer was to be really careful about the analogies that I chose so that they would build on each other. So that first of all, they wouldn't be isolated from each other because it's easy to choose an analogy in chapter 5, which in some way is in contradiction to the analogy you chose in chapter 7. Being very careful that all the analogies are self-consistent is very important. And also being sure they're all consistent with the equations. I didn't want to use an analogy which then I would have to embarrassedly say, well, actually, that's not true. I mean, I had to in a few places, even then, because for the same reason as I was describing, for our first year students, you have to start with what you can explain at the beginning, and then you add to it. And at some point, you can explain something more complete and say, okay, the analogy I used earlier is not complete, and here's why. But you have to be sure to do that instead of leaving people hanging.
One figure that plays a huge role in this book is my friend Galileo. And as many listeners to this channel will know, he is perhaps my favorite physicist. So much so that I made a 22-hour-long audiobook, the first one ever, with my friend Carlo Rovelli and Lucio Piccirillo. We read the dialogue over 22 hours. I think it's quite fascinating when we think about things like the notion of Galilean relativity. And he's really not given that much credit. And because you are a master educator, I've often wondered, and I'd love your take on it, why we don't teach, we start off with inclined planes and pendula and things like this. But why don't we teach the controversy, Matt? Why don't we teach? This is the book that got him in prison, the dialogue. This is the book that caused him to spend the last 9 years of his life in a pretty sumptuous prison outside of our Chetri, Italy, which I've been to many times. I actually hosted a conference on the 100th anniversary of Einstein's relativity. But Einstein in the book called him, one of the greatest contributors to Western thought, and he was a man of no small ego. Why don't we teach to our students the controversy that surrounds this book, instead of talking about inclined planes, and also teach his blunders? In that book, he goes to such great lengths to prove something which is ultimately true, that the Earth goes around the sun, pretty much. But he interjects the wrong evidence, which is the Earth's tide. So talk about Galileo. What does he mean to you? What is his importance? And how can we leverage his fascinating life and just storybook, kind of circumstances to better educate our students?
Well, I mean, it's a great question because Galileo was one of the most important figures in Western science. He sits within a context of Kepler and Newton, Huygens, a few other people. But there is something about him that is unique in two senses. First of all, he was a great creator of machines. He could create telescopes. That's why he could be the first person to look at the sky. When the telescope was invented, he made his own and quickly was ahead of everybody, or at least at the forefront, so that he could do things that you can do today with binoculars, but nobody could do before, and discover all sorts of things about the planets and the moon and the sun that were just out of reach of the human eye. And so he was a remarkable person for being in the right place at the right time, but also having the instruments which allowed him to take advantage of that. That's a lesson for science, that if you're in the right place at the right time as far as technology, and you have a prepared mind, that's when you can do really special things. But also remarkably, he spent a lot of time on what we in physics would call mechanics, how things move and why they move and at what rates. And he had all sorts of clever ways of doing experiments to figure out the effects of gravity on falling objects. I won't go into that in any detail, but he had, of course he wasn't perfect. Nobody in the history of science has ever been. Newton made mistakes. Einstein made mistakes. Mistakes are going to happen, but you have to judge a person, I think, by their achievements. And he has so many. What's essential in this book is the discovery that the laws of nature don't depend on how fast you are moving if you are in steady motion. This Galilean principle of relativity is I think, the question you asked about whether we should teach about the controversy, that's an interesting one. Maybe so. I would also want to point out just how important the principle of relativity is in the history of the human species, because that's what explains one of the biggest conundrums that human beings ever had, which is, if the Earth is spinning or going around the sun or doing any of these things, why don't we feel it? And he gives the answer. There's hardly a more important question. And that's the beginning of all of astronomy in the modern world. Once we realize that, oh, this motion could be happening and we wouldn't know it. And even to the point that today we know we're going around a galaxy which is flying through the heavens towards other galaxies and away from others, and we don't feel any of it. Galileo told us why.
Yeah, and of course he was, brilliantly blundering, made brilliant blunders. Even when he made a blunder, it was right, just like Einstein. I like to encourage my students to strive to be like Einstein when your blunders are...
When your blunders are as good as your best work, yeah, it's really nice.
Your biggest blunder is to say your biggest blunder was inserting the cosmological constant.
Right.
Right, so aspire to such great things. Okay, so the impossible C is obviously motivated by, one of the greatest fibs, which is that the analogy given even by the Nobel Committee and my late great, professor Jerry Guralnick at Brown, and many others, was sort of that the Higgs gives mass, the Higgs boson gives mass to particles, and it's sort of like this ether, which can then be used to generate these interactions. And I want to get into all the ways that that's wrong. But before we do, the thing that struck me reading it and knowing a little bit about the history, I mean, I never met, Peter Higgs, but I knew Jerry very well, and Carl Hagen and others. But, in the 1960s, the milieu that was surrounding people was not, let's make this consistent with Galilean relativity. It was that the electroweak, theory had these, seemingly gauge violating, entities, something, that was not permissible under the standard symmetry of SU2 cross U1. So how do you, kind of explain historically, how they overlooked what you are, presupposing, and justifyingly so. But this wasn't the motivation. Let's talk about symmetry breaking, how the actual, mechanism was proposed and discovered in the 1960s. And then, what's wrong with at least the conventional explanations to the media, et cetera.
Yeah, I mean, just to be clear, the physicists knew exactly what they were doing. The problem has been, the problem that motivated part of the book is that our ability to explain that to non-experts has been less than ideal. It did involve some tricky math. I mean, that's why someone like Higgs or Brout and Angler and Guralnick, Hagen, and Kibble, these had to be world-class physicists to notice what, in retrospect, doesn't look that difficult. But at the time, they had to understand quantum field theory very well. It was a new subject. So the puzzle was that people knew how to do quantum field theory with photons, with light. And in the very late 50s, it was proposed that maybe the weak nuclear force and all the different things that are associated with it come from photon-like particles that have mass. And the puzzle was, it wasn't obvious how you could take a theory like the one used for photons, and give mass to those particles to make a theory that would work for the weak nuclear force. That was the basic problem. Well, except that's ahistorical. Because in fact, neither Brout and Angler nor Higgs was paying attention to that problem at all. That application of the Higgs idea came in 1968 from Stephen Weinberg and Abdus Salam. But in fact, at the time, there was another problem involving photon-like particles with mass, for which the Higgs mechanism turns out to be completely irrelevant. As always with history, it's really complicated. It turns out there are particles that are they're like protons. It turns out they have quarks and antiquarks in them, and they have spin 1 like photons, and they have mass. And Brout and Angler were actually interested in that, what it would involves the strong nuclear force. It turns out not to be relevant for that at all. So the history is quite subtle and amusing. But the end result of 10 years of ins and outs was that by 1968, there was a proposal that the weak nuclear force is explained by particles that are photon-like, they have mass, and they get their mass from what is now called Higgs mechanism, although the Higgs mechanism was also invented by Brout and Angler and by Guralnick, Kibble, and Hagen. So the mathematics of that was clear enough. It's just that nobody had a good way of explaining it to some science journalist because it was, looked like complicated math. And what I've done in this book is kind of take advantage of the fact that while the details of how you give mass to a photon-like particle, the so-called gauge symmetry and the symmetry breaking, which isn't really breaking anyway because the gauge symmetry isn't real, and all that's so complicated, and somehow the part of the Higgs field gets eaten by forget that. That's not actually what people want to know. People want to know how do things get mass from a field? That's the basic physics question. The mathematical details are not the point. And it's also true that the focus on symmetry breaking, which was, and magnets as an analogy and so forth, that's really kind of passé. And a lot of theoretical physicists do not think that way anymore. But the issue of how things get mass, that's critical and also really the essential thing, because if electrons didn't have mass, if they didn't get mass this way, there'd be no atoms. So when you focus the attention on the question, how does a field give something else mass? It's less specific than the weak nuclear force and the details of what happened in the 1960s, but it is the key idea. And the key idea there is that, well, it involves combining a bit of relativity and a bit of quantum physics and a bit of waves and standing waves in particular. And you can do that in words and pictures. And that's what I attempted to do in the book. It takes a little while. I mean, that's why the book is 300 pages, but it can be done. And it doesn't require complicated mathematics to see it. It just requires learning a few unfamiliar things, which are not actually that far from what we know. It's just for whatever reason, we leave out a couple of steps in our explanations, and so I had to add them in.
And I want to dovetail into a topic you just mentioned, which is symmetry breaking. And in the book, you discuss past guest and upcoming future guest, again, Brian Greene, and his epochal book, The Elegant Universe. And I should say it's the 25th anniversary of that book.
Very famous book.
Yes, very famous, and he's coming back on the show for another Brian versus Brian episode. In your book, Waves in Impossible Sea, you say that the elegance concept is desirable in mathematical formulae that describe the universe. It's not a, quote, defining characteristic of the universe itself, and you caution against projecting human biases for elegance onto the universe, arguing there's no guarantee the universe adheres to our aesthetic preferences, and you point out the Higgs field, which is a crucial element of this book and the standard model, is rather inelegant. And I want to first get your reaction. We'll zoom in on your face. My fourth book, I'm almost done with my third book. I'm going to publish my fourth book, which will be getting back to cosmology and astrophysics and the life and impact of Jim Simons, among other things. And that is, I'm considering calling it the grotesque universe, because actually, I make the point that it's actually the broken symmetries that allow us to have this conversation, right? And I wonder if you could say more about that. If the universe were perfectly elegant, as Brian, would seem to desire, the other Brian, we wouldn't be here having this conversation, right? So, talk about the kind of amazing nature of the so-called fine-tuning problems of matter, antimatter, all the asymmetries that allow us to exist.
Well, this is a very rich and complex subject, so I don't know how deeply we can go into it.
My audience is the deepest and the most intelligent in the known multiverse.
It's more a matter of time. We could talk about this for 2 hours. First of all, there are many different types of symmetry, and so even that's a little complicated. But there is always the issue about whether a symmetry exists in the equations, whether it exists in the physical objects, and you could have one and not the other. There are often symmetries which are accidental. The galaxy is not a perfectly symmetrical object, but the Earth is remarkably, almost symmetrical, right? It's close to a ball. Where did that come from? Well, it comes from the equations for gravity, which are symmetric. But not all things made by gravity are symmetric. The galaxy isn't. So the way that symmetries go from equations to objects is always a long story. And so just because you see some objects that are symmetrical, or you see some objects that are behaving symmetrically, or you even see some behaviors which seem to be symmetrical, that doesn't mean that underlying it that symmetry is somehow fundamental. It may be an outgrowth of more complicated things. And so one has to be very careful about assuming that the universe must be symmetrical. One also must be careful about assuming that the universe is beautiful from a human perspective. And one must be careful about thinking those two things have to be the same. I mean, those are two different conceptual ideas, right? Could be beautiful in some asymmetrical way. When Brian speaks about the elegant universe, he is speaking a language which many scientists have spoken, probably all the way back to Newton, certainly since Einstein. And there, the idea is that the equations should be in some way elegant, beautiful, symmetric, some intersection of those ideas, which does not mean at all that the solutions to those equations will be symmetric. Just as the laws of gravity are symmetric in all directions, but the galaxy is not. So the fact that our lives depend on there being many asymmetric facts about the universe is not necessarily in conflict with the idea that the universe's equations might be perfectly and beautifully symmetrical. So those are two different issues. Now then, when you ask what is Brian talking about, he's talking about the equations. And he is making certain assumptions about the universe's equations should be elegant. Well, maybe the fundamental equations are, but maybe the equations that Brian is looking at, maybe the equations that string theory is sort of on the edge of, the equations of quantum gravity, maybe they're not. Certainly, we have a history for this. Einstein wrote down his theory of general relativity partly based on an aesthetic criterion. He wrote down the simplest equations that he could, that would be consistent with some principles that he had developed. And we know, in a way that perhaps he did too, I don't really know that history, that there were many more terms that he could have written down. And in fact, we think those terms are actually there. In string theory, they would be there. So his term involves the curvature of the curvature scalar, but you could have the curvature scalar squared. You could have the curvature scalar cubed with derivative, with spatial derivative. You could have all sorts of things. And in fact, we think we do. So at any given stage of physics where we're writing down the equations we understand at the time, assuming that these are the ones that should be beautiful and symmetric, is making an assumption about how fundamental those equations are. And we've been wrong many times about that. Well, Einstein's equation is not thought to be fundamental anymore. But when he wrote it down, one might have thought it was. So, these criteria for elegance and aesthetics and symmetry and so forth, they are constantly changing with time. And if you look at that history, you can see those changes. And so I think that should make any practitioner and anyone evaluating the progress of science and interested in the progress of science very skeptical about those sorts of assumptions being applied by physicists onto the research that they're doing at any given time.
Hey there, do you want to surround yourself with knowledge that I've gleaned from conversations with over 20 Nobel Prize winners, 4 billionaires, multiple astronauts, and more? Well, I want you to subscribe to my Monday Magic mailing list, where I send out 5 different nuggets of wisdom to start your week off right. The things you're most interested in, including my conversations with thought leaders like Matt himself. So to get that and enter to win a real 4 billion-year-old piece of space schmutz, a real meteorite, sent to you directly, not by gravity, not by waves on a cosmic sea, but by the US Postal Service. I'll send it to you. If you join my Monday Magic mailing list and happen to win, it's at briankeating.com/list. But you're guaranteed to win if you live in the United States and you have a .edu email address. And that link is briankeating.com/edu. Sign up now and join me through the mysteries of the cosmos and beyond.
One of the things that, kind of always has seemed like a trick to me, but it comes up in the book, but in relatively less detail because I think it is so complicated. But knowing your pedagogical gifts and the various encomia that you did receive, I have to take my podcast prerogative and ask you to define renormalization and why it matters. Because to me, I'm just a simple experimental cosmologist. I build telescopes, Matt. So it's always seemed like a trick. Like I could never get away with it. In fact, in experimental physics, as you talk about in the book, you talk about the discovery of the CMB, and it plays a role, and that's what I do, obviously. But there was a man, and his name was Edward Ohm, and he was using the same Holmdel antenna, not far from you on the East Coast, that Penzias and Wilson used. And instead of analyzing the data the way that Penzias and Wilson did and looking, he saw that there was a 3.2 Kelvin excess, which is what he measured. And he said this must be just from the various statistical errors conspiring to add together, and so we can effectively convert that to a systematic and just subtract it. So he renormalized his data and lost the Nobel Prize. So he's the original, kind of person who deserved to write that book that I ended up writing. But tell me, renormalization seems like a trick. You get these divergences, you subtract infinity from infinity, and then,
right.
God, it works out perfectly.
And part of the problem is that renormalization has nothing to do with infinities at all. The infinities are an artifact of doing quantum field theory, assuming space-time is continuous. It's totally irrelevant. And so part of the problem of explaining it is that the first thing you have to do is separate the infinity question from what renormalization is. Even to answer the question what renormalization is a little complicated because there are a few different types, but I'll just focus on the one that you're implicitly asking about. Even if I take a very simple physical system, like a pendulum, I have to worry about renormalization there in a sense. Because if the pendulum has a very small amplitude of oscillation, then I can do freshman year physics on it and I can calculate the frequency. But if it starts swinging more, now the fact that the equations for a pendulum are not exactly the same as the equations for a spring, the equations for a simple harmonic oscillator, starts to matter. And so the frequency of oscillation will change. That shift in the frequency is the first step towards renormalization. Now, if you imagine, I take not one pendulum, but I take one pendulum that's interacting with a bunch of other pendulum, like they're all connected by springs. It's really complicated. And they don't follow the usual rules of springs. Then if I look at the frequency of any one pendulum, I may discover that it's been shifted by a lot by its interaction with all the other pendulum. And so if I calculate like a first year physics student, I think the frequency is going to be this, but I discover instead it's this. Now, how do I deal with that? I have to calculate that effect. But in particular, if I want to now understand the properties of this pendulum that's swinging much faster than I expected, and I try to understand it by saying, well, let me start like a simple freshman with a very wrong oscillation frequency and try to calculate all the effects that this pendulum, all the things that this pendulum might do, all the phenomena that it might do, starting with this completely wrong picture, my math is going to never give me good answers. So in order to be able to calculate what this pendulum will do, I'd better first shift from what the freshman would pick to what it actually does as a first approximation. That is renormalization. It's about being smart. It's about saying, well, don't use the wrong first approximation. Use a better one. When we talk about the mass of an electron, what we're really talking about is the resonance frequency of the electron field. The same issue applies. If you try to be naive about what the electron field's frequency is, ignoring the fact that the electron interacts with photons and with all sorts of other fields, you don't account for this effect, which shifts the frequency and therefore shifts the electron mass, you're going to get completely the wrong answer. Now, that would be true even if you worked in a quantum field theory in a space-time that was finite. The reason you get infinities has to do with the details of how we do the math, where we ignore gravity, we assume space-time is flat and continuous, and then it's like having my first pendulum interacting with an infinite number of pendula, and then it's not surprising the shift is infinite. But the important thing is you have to do the shift. That's the renormalization, because otherwise you're just doing something dumb. The fact that the shift is infinite is a detail that has to do with the way we set up our calculations. But in the real world, it's probably finite. Nevertheless, the renormalization is necessary. Otherwise, you're just going to get wildly the wrong answer.
Another topic that comes up a lot in this book and is near and dear to my heart is the luminiferous ether. And you have another type of efferous ether that I'll invite you to speak about. But I want to
Do I have to say it out loud?
It's not dirty, you know.
It's just ugly.
I talk about, panspermia a lot on this podcast. So I want to take you back to 1961. So there's this eminent physicist, James Clerk Maxwell, and he's working away, and he comes up with this incredibly detailed, accurate, highly mathematical, quantitative theory of electromagnetism of, between 4 and 8 different equations, depending on whether you include the auxiliary, source equations as part of his, and he comes up with the concept of electromagnetic waves. And this becomes very startling to him because he doesn't see how a wave can get from the sun to the earth without going through a medium. And so he proposes or hints at this luminiferous ether, which has electric virtue, he calls it. And he goes through kind of a mechanistic derivation of its properties, including gears and whirlpools and pendulum, all sorts of crazy stuff. And it's beautiful. And it makes a lot of sense until, 49 years later at my alma mater, Case Western Reserve University, Michelson and Morley, so-called disprove that there's an ether. The first question I want to ask you is, did they really disprove it with the Michelson-Morley experiment? And by the way, there's nothing that says disappointment, disillusion, depression more than my alma mater feels because they can't find the exact experimental apparatus. They have a picture of it, but they don't know exactly where it is in Rockefeller Hall or in that area where I spent way too many hours of my life. So there's quite a good deal of the dejection. I guess, 1,000 years from now, they won't be able to find CERN either. But didn't Romer and others, when they measured the speed of light using the eclipsing transits of Io and Ganymede of Jupiter, why wasn't that sufficient to, at that time, 100 years before Michelson and Morley, disprove that the speed of light is time-dependent or motion-dependent on the Earth?
I haven't gone through that exercise. I presume that the accuracy just wasn't sufficient. I mean, the point of Michelson's invention was that the precision with which the measurements could be made allowed for detecting a change in motion, which is really rather small. After all, you're comparing light speed at 300,000 kilometers per second to the motion of the Earth around the sun from one period to another, from 6 months apart, which is much smaller, which is a small fraction of that. And so a certain level of accuracy would be needed. And I don't believe that anyone had that accuracy at that time. If I'm wrong about that, you should let me know. But my understanding is that what Michelson did was make an experiment possible that nobody could have done previously. The precision was just not available. And in fact, the first experiment he did was still not quite precise enough. So it really wasn't until 1887, if I remember correctly, that they really nailed it. And at that point, it became very puzzling because, after all, people really understood waves. By the 19th century, they knew how sound waves worked. They knew how water waves worked. And they certainly knew that if there is a medium for these waves, and all waves have a medium, something must be waving. That's the assumption. Then you should be able to tell whether you're moving with respect to that medium or not by looking at the speeds of waves that come from different directions. And that's essentially what Michelson did. And finding no effect, well, the only really sensible, simple explanation was that somehow the Earth drags the ether with it. And so we're not moving through it locally. Even though the Earth is moving through the ether generally, somehow we are not moving through it locally, almost as though it's a boat that drags the water with it. And then you wouldn't notice that you were moving through the water. Well, it's a reasonable idea, but now it's getting pretty messy and complicated. But, it wasn't the only problem in physics, so people kept working on other things, and some people thought about it and some people didn't. And then a young man came along and looked at some of the ideas that people had over the past 15 years since the experiment had been done and said, I don't think you're thinking about this right at all. So what he said at the time was, there's no ether, there's no need for an ether. Space and time work differently from the way you think. And that's why Michelson and other measurements have seen nothing. This is what we teach. We always teach in freshman year. But then there's something we don't teach, which in a way I only appreciated later in my career because I'm not a gravitational theorist. I'm more of a particle physicist. But what Einstein said 10 years later is well, wait a second. That's not really what I meant. What he said was, actually space is an ether, like the luminiferous ether. You just can't measure that you're moving through it. The reason I think it's so important that I think we should teach this, I think it's so bad that we don't teach this, it's a completely different answer to the problem. So Michelson asks the question, hey, I'm not seeing any effect. Why don't we see our motion through the ether? Einstein says first, well, there is no ether. And then 10 years later, he says, no, wait a second. It's possible for there to be an ether that for which you cannot measure your motion, which is a much more radical statement and really transforms the way we think about the universe. And we're still dealing with that 100 years later.
I looked up while you were speaking using Perplexity AI, the choice of artificial intelligence for, no, I'm just kidding. I'd love to be sponsored, but none of these places won't. So the history of measurements, Ole Romer, 1676, insanely early, 220,000 kilometers per second, 27% lower than the actual value. James Bradley, 1729, got a value within 0.4%, which is incredible, using stellar aberration.
Yeah, that's remarkable.
It's
not good enough.
Well, I mean, I want to ask you about that. Let's say Foucault did better, Fizeau did worse, but they were all within, under 5%, in some cases 0.6 and 0.4%. So let's say it was, you saw a deviation at the 0.7% level. So it's just barely 1 sigma or 2 sigma in the case of Bradley. How would you have explained it? Let's go back in time. Let's do a Gedanken experiment and go back to, 1886. You got these measurements, Matt, and they differ by less than 0.5% from complete uniformity with regard to the Earth's motion throughout the cosmos. You would have to propose a highly finely tuned ether velocity, would you not? Or am I wrong?
The natural expectation would have been that you would see a yearly fluctuation that would have been a fraction of a percent, a much, much smaller fluctuation daily, which would have been much harder to measure. And that the explanation for it would have been that the Earth's motion is varying. Circular motion is causing a sinusoidal variation in our motion relative to the ether, and we would see that effect. But one could have imagined additional effects coming from the fact that the Earth is moving through the galaxy is moving through, it could have been many effects that could have been observed.
But I think that makes my point stronger. In other words, I'm saying your conclusion would have been that we're almost stationary with respect to the ether rest frame.
Oh, is that what you're saying? Yes.
Yeah.
And look, at that time, they didn't know about the galaxy, right? They kind of knew, but they didn't really understand what it was.
They thought the galaxy was the universe. I mean, Einstein thought the galaxy, and that's all they knew.
Right. And so there's
1923, right?
Right. So there's all sorts of questions which if you ask them in a different historical order, you could certainly have had, a different discussion. I think it's hard to have those hypothetical discussions because, you have to be more specific about exactly what we didn't know at some particular time. Historically, I think they were just expecting to see a variation. After that, they had all sorts of questions they would have to answer because the really strange thing, right, is that whatever this ether is, it has to have the property that on the one hand, its waves are light and they interact quite strongly with ordinary matter, right? They don't go through the Earth. And yet the Earth goes through the ether without any drag. How do you make those things consistent? So even if you had a model for the ether and even if you measured that you were moving through it, you would still have the problem. How am I going to make sense of this stuff? And the fact that the real picture is somehow that the universe is kind of ether, sort of. It's kind of a substance, but kind of not. It's impossible to see because it has these weird properties. And that we and the Earth are made from waves. That makes it a little easier to understand because waves can go through substances just fine. You and I can't go through the Earth. And the Earth wouldn't be able to go through the kind of ether that Maxwell was imagining unless it was made from waves of that stuff. Because earthquake waves go right through the Earth. Sound waves go right through the air, even though you and I can't go through it at hundreds of miles an hour. So the whole notion of how the universe is put together comes out of this Einsteinian period. We begin to realize, okay, the picture has to do with waves moving through something like a substance, but not quite. And, that's where we get our title for the book, right? So it's not like I understand how this works. I'm just telling you this is what the equations say. We don't understand how it works.
Another character whose presence is felt by his absence is Ernest Mach. I don't recognize much from the book about him, but he seems to have had a huge influence on this guy. And sort of the notion of the impossible C, it's kind of maybe could be thought of as, all the Higgs field in the entire universe, which would then be that against which you measure relative motion, inertia, rotational momentum. So talk about Mach and why he didn't play a role.
Right. And I do want to make a distinction between, I've been talking about space as an impossible C. The Higgs field is an addition to that. But fundamentally, the question is about space itself. So I don't want to give the impression that the Higgs field is the impossible C. The Higgs field takes place in something that's already an impossible C, namely space itself. Let me say, first of all, I'm not an expert in Mach's writing. I only know what I know through what Einstein describes about it and what a few other philosophers have said. So I'm not really speaking with authority here. But my impression is that one of the important things that Mach was focused on was the question of what does it mean that the stars, the distant stars, give us a frame relative to which we can measure our motion? And today, that's what the cosmic microwave background does. It provides a natural way for us to measure our motion. And so it's a very important question to distinguish. What does Galileo's principle say, which is that steady motion cannot be measured? Why is that not in conflict with the statement that, well, there's this cosmic microwave background, which we can use, as Mach would have suggested, to measure our motion? Are these things not in conflict? And it is a subtle point. And the point is that, yes, you can measure your motion through the CMB. And in doing so, you are measuring your motion relative to the CMB. You're not measuring your motion relative to space. That's a different thing to do. And one way to see that is block out the CMB. Put yourself in a big metal cage. CMB doesn't come in. Now try to measure your motion. And you won't be able to do it. That's a statement about how the universe works. The fact that if you block out the starlight, block out the CMB, block out the specific properties of what the universe is full of, and now you ask what the universe is made of without all that distraction, now you cannot measure your motion. That's the principle of relativity that Galileo brought to our attention and that Einstein preserved in his theories of space-time and gravity. Mach, in the end, has a very important point to make, but it's also very important to set it aside. It's not the right point. It's not the point that troubles theoretical physicists today.
One field that plays some small role in the book is the inflaton. And I want to ask you...
Very small.
And I think that's for good reason. I mean, a lot of books, and at times I found that it might border into, supposing that inflation is true, which we, if it was, I wouldn't be able to butter the bread around the Keating house because that's exactly what the Simons Observatory is looking for. So, it keeps full employment around here. That it hasn't yet been discovered. We claim we detected it, 10 years ago, but we're not going to get into that. So inflaton. I always, thought for a long time, maybe it doesn't exist. I mean, after all, we don't know of any spinless, scalar fields. Now we have the Higgs field. Did the Higgs discovery, the Higgs boson discovery, which we should delineate is not the same as the Higgs field by any means. That's a core tenet of this book. But the discovery of the Higgs boson itself, did that give more Bayesian confidence? Should it increase my confidence that we will eventually prevail in our search for inflation?
Just as an electron is a vibration in the electron field, a Higgs boson it's a particle or a wavicle. It's a ripple in the Higgs field. So if you discover the Higgs boson, that tells you the Higgs field exists in the same, similar way that if you can hear sound, that's some indication that there's air in the room. The inflaton is a Higgs-like it is a speculative notion that there's a Higgs-like field, plays a role much earlier period in the universe when it was much hotter or much more dense, or, well, inflation is complicated. Let me start again with that. The inflaton is supposedly responsible for the universe growing very rapidly to its large size, and afterward setting the hot Big Bang in motion, making things very hot and dense as they are believed to have been. And so your question is, once you know that a Higgs field, which is a particle without spin, it's the only field of the corresponding field, the Higgs field is the only field of its type in the Standard Model, and it's similar to what if an inflaton field would have to be, does it give you more confidence that inflaton fields could exist? And I would say that actually we knew that they could exist already. And that's because there is already a Higgs-like field in the Standard Model. It's just not an elementary field. When the strong nuclear force becomes strong and protons and neutrons begin to form as the universe is cooling, there is a combination of quark fields and anti-quark fields, which acts very much like a Higgs field. This is not something I covered in the book because I didn't really need it and because it's a bit of a subtle topic. But this is why theoretical physicists knew you could have Higgs-like fields. They just didn't know if you could have elementary Higgs-like fields. And we didn't know if the Higgs field would be elementary. So far, all the evidence is that the Higgs field that we've discovered through the work of the Large Hadron Collider probably is an elementary field, or at least at the scales that we can see now. But the inflaton, we have no idea. It could be an elementary field. It could be a composite field like the one we have in the strong nuclear force. So I would say that as far as inflation generally, it doesn't particularly change the priors, the assumptions. But if you like theories of inflation where the field is elementary, maybe it helps a little bit, yes.
I want to read another quote, and I'm going to ask you, is it from Deepak Chopra, Stefan Alexander, or Matt Strassler?
Oh, that could be hard.
We can ask the question that the students really wanted the answer to. What is the secret chord, the underlying harmony of the universe? Who wrote that?
I did.
Aha. Okay, so Stefan's question, he is the shadchan, the matchmaker that put us together. So props to my brother Stefan. He says, Matt, he wants to know from you, is the universe improvising?
And that is very much Stefan's question. I think one of the things that makes Stefan a special person, a special scientist, is that he is willing to entertain connections that to most physicists might seem very tenuous. And in this book, and not necessarily what I'll do in other books, but in this book, I was being super careful to stay away from things that were speculative. I'm going to answer in two ways. So from the language of this book, I would say, no, the universe is not improvising. The universe is not playing music. The universe is a musical instrument. Things happen on it. Music is happening, but that's what the stuff is. The vibrations of this instrument are things like electrons and quarks. There is no coherent musical plan. It's not in tune. There's no sort of harmony there at that level. So from the point of view of the book, that's what I'm going to say. Now, from the point of view, the larger question about music and resonance in the universe as a whole, it's fun to think about the fact that the universe is not a simple, pre-written, set in stone kind of musical object. I mean, quantum physics is not really easy for human beings to think about. And, Stefan would like to think about that as improvisation. I'm happy to entertain that because again, he's an original thinker and we need original thinkers. It's not a direction that I know quite where to go from my own point of view, because for me, music is so much about the human interaction with vibration. It's really about perception and about harmony as we experience it. And so for me, improvisation is really more about, setting that up first and then going further. Stefan has good ideas and I'm happy to promote them. I think your readers should definitely read his book.
Okay, so I got to ask you some rapid fire questions. Do you believe there are elementary spin 3/2 particles? And if so, why? If not, why not?
I have no idea. And I'm not the kind of person who makes guesses about that sort of thing. I will say that I see no reason why they shouldn't exist. But there's also a distinction between spin 3/2 particles that could have been massless versus ones that are inherently massive. And I think ones that are inherently massive are pretty likely. One that could have been massless, that specifically has to do with supersymmetry. I have no idea.
As you know, one of the main goals of cosmological research is to make particle physicists irrelevant. And one such way would be to discover the mass of the 3 elementary particles whose masses are currently unknown. They're bounded from below and from above, but they're not detected. And those are neutrinos. If I tell you a year and a half, please God or Gaia or whoever you want, Simon's Observatory and our partner institutions, colleagues, collaborate, we have detected the mass of neutrinos. It's, the minimum mass in the normal hierarchy, and 3, 4, 5 sigma, whatever it is. Do you think your fellow CERN dwellers, LHC purveyors will believe a measurement of a fundamental elementary particle's properties measured by cosmologists of all people?
I don't see why the reaction will be particularly along the lines that you just suggested. The question is really, as always, what is the nature of the measurement? What is the degree of confidence in the measurement? And, can it be verified by other groups? So, sure, nobody will believe it the first time because nobody believes any new technique or measurement the first time. And there's all sorts of things that don't get believed the first time. But that's not because of who did it or how it was done in principle. It's just that, lots of new measurements are mistakes. That's why we have to verify them, right? We only trust things when they've been found by 2 or 3 different groups. I'm not sure we would have trusted the Higgs discovery if there hadn't been 2 groups to measure it. So at least not right away, right? It would have taken a while. So on day one, the answer is no, but I mean, most people aren't going to believe it, including cosmologists. And, over time, though, it's really a matter of whether the uncertainties get smaller and different groups doing it different ways come to agreement. Now, of course, this will be complementary to other particle physics experiments, which are measuring other aspects of neutrino physics. So at some point, there will actually be a possibility of comparing some of those, both the cosmological and the particle physics measurements, and that will then add further confidence. But, probably it'll take 10 to 20 years before people are really confident, no matter who does it first, right? These are hard measurements, and that's why we haven't discovered the neutrino mass yet. It's hard. So when it's done, there'll be a lot of controversy, but I don't think it'll be specific to, particle physicists versus cosmologists.
So the name of this podcast is Into the Impossible, and it derives from the famous quote by none other than Arthur C. Clarke, and I'm the associate director of the Arthur C. Clarke Center for Human Imagination at UCSD, and so I love books that have the word impossible in them. And one of many of Sir Arthur's quotes that has the word impossible in it is, "The only way of discovering the limits of the possible is to go beyond them into the impossible." And you can add C after that if you like. But I want to use another a quote of Sir Arthur that also uses impossible, and that's the following. "But when an elderly but distinguished scientist," you are distinguished, "says that something is possible, he or she is very likely to be right. But when he or she says something is impossible, he is very much likely to be wrong." Matt, what have you been wrong about? What have you changed your mind about?
I really didn't think that space-time was an emergent phenomenon until the discoveries in string theory that showed that it can be. And then thinking about relativity again in that context and seeing how in the context of string theory, we have examples where you start with a quantum field theory and you rewrite it in a way that you get gravity and relativistic causality in extra dimensions to just come out of the math. And that there's some relation between the space-time in that second picture and entanglement, quantum entanglement in the first picture, that some of these two pictures are the same. That has made me very skeptical that space-time is a fundamental concept. And that's very important because, after all, fields exist in space-time. So if space-time isn't fundamental, then fields are probably not fundamental either. In general, there's probably something deeper going on. And that's probably one thing that I changed my mind about. That now, I'm not sure I would have said it was impossible for space-time to be emergent, space to be emergent. Well, okay, space and time are different in the sense that I understand how space can be emergent. I still don't understand how time can be emergent, but that's even more important. And after all, for Einstein, they're really tied up together. So I would say that these are questions which trouble me today that probably wouldn't have troubled me 25 years ago.
Very good. Well, Matt, this has been an impossibly delightful conversation. And I want to refer people to your Twitter account, and we'll have links to all your stuff in the book as well, and your blog, which I am delighted by as well. Any other final thoughts you want to leave the audience with before we break up?
Maybe just that, I think one of the things I'd really tried to highlight in the book is that the deep and fundamental questions that we physicists are facing, despite the fact that physics has a reputation of being a really, really complicated subject, the questions we face are not that complicated to understand. And one of the key points of the book was to try to strip away what is so complicated about physics and make it clear just how basic and fundamental the problems of physics still remain.
Matt Strassler, thank you so much for your valuable time and your wonderful contribution in this delightful book. And I hope we get to meet in person, and we'll do a part 2 someday.
All right. Well, you can ask all the other questions we didn't get to.
Bye, my
Thanks
friend.
so much, Brian.
Bye.
Hey, if you watched all the way to the end, I know you'll love my interview with the biographer of Peter Higgs himself, Frank Close. And click here for a playlist of the best episodes from the past few weeks. Go on, push that button.